Welcome back to part 2 of lesson 8.4. Before we proceed on to the second part, I just want to go through some important details from 8.4 part 1. Remember that logs find exponents. Also, our rewrites are very important. When we get them into exponential expressions, it allows us to move forward with the problem. Common logs are base 10, natural logs base e, and we like those because they can be evaluated easily by just using our calculator. So let's move forward and let's talk about part 2 of 8.4. We are going to continue with log functions. In particular, today we're going to work with special log values and also some inverses of logs. When we do this, these special log values will help us to evaluate the log quicker and a little bit easier. And then finally, to the inverse of log functions might be something you're familiar with because we have done inverses in the past, so some ideas are going to carry over in this lesson. Special log values are awesome because they allow us to solve log expressions quicker and easier. And I know you like that idea, so let's see why this log base b of b to the x is going to play out the way it does. If I do a rewrite, something I am familiar with now, we know that we want to set the log expression to x, and when I do that, the base of the log, which is in yellow here, becomes the base of the exponent, log sal for exponent, so this blue x now becomes the exponent of the base of the log. And what does it equal? It equals the number that's in orange, this b to the x. And look what we have here. We have b to the x equals b to the x. So what does that tell us? It tells us something very important and very easy to see, that the two exponents that we have here, the one that log solves and the one of the number, are matching. So that means that in our example 1, the log base 8 and the 8 of the number, if they match, it means that we already know the evaluation. It means that this log is evaluated at 9. And that's our answer. So that's how easy it is. A match here means that we already have our answer. I knew you'd like that. So let's take a look at example 2. And you knew I'd step up my game a little bit here, and I did. I have a log base 5 of 125 to the x. And we don't have anything matching here. We need for these two to match, and they don't. But I think you know of a way that these can match. Do you know what we can do to this 125 so that these match? You said to bring that base down to a 5 to the third, didn't you? So 125 is re-expressed as 5 to the third. I'm going to go ahead and write what I didn't use, and let's see what happens here. Now don't forget that that was 5 to the third, and there was the x already out there. So that means that these cancel, and I'm left with the simple answer of 3x. That's my answer. So just to recap what happened there, I took this 125, I rewrote it as 5 to the third. The 125 was already to the x power, so when I incorporate this 3 with the x that was already there, I get 3x. The 5 of the base and the 5 of the log cancel, and I'm left with 3x. And let's do our last one here. If I have log 10 to the x, watch what's going on here. We learned that if the log doesn't have a base there, it is understood to have a base of 10. And now look what happened here. We have a matching pair. They cancel. Our answer is x. So see how simple that is? If we just pay attention to this rule, we can get things done quicker and easier. All right, now why don't you give this a try? See if you can come up with the answer to evaluating this log base 2 of 16y. Press the pause key, make your computation, come on back when you're finished. All right, so welcome back. Let's see how you did. Here's the answer to your problem. The answer is 4y. Our second special log value rule is actually the opposite of what we just did in our first one, because now we have an exponential form. You can see here that we have a base b, and this whole log b of x is the exponent. So that makes this an exponential expression. If I want to transfer that to a log expression, I'll bring back something a little bit easier for you to relate to. 5 squared equals 25. If I want to write that as a log, I would do the rewrite as log. And the base of the exponent becomes the base of the log. I'm going to go ahead and make my 25 the number of the log, and it equals the exponent, which is 2. Logs find exponents, so it makes sense that the 2 is on the other side of the equal sign. Now let's do the same thing over here by starting off with setting everything to x, and then starting with our rewrite. Let's do the log, and now let's take the base of the exponent and make it the base of the log. We have to take our x and slide it over next to the log right now. That's the same as the 25 up there in our example. And the power goes over to the other side of the equal sign. Now if you look very carefully at what we have right here, you will notice that the left side of the equal sign is exactly the same as the right side. Log base b of x equals log base b of x. What does that tell us? It tells us if we just don't look at this log base b right now, you're to understand that the x equals the x. And that helps us because when we go to evaluate example 1, and I see that the base of the power equals the base of the log, and you're going to evaluate that simply by saying the answer is x. That's how simple this is. Let's take a look at example 2. If I have a base of 10 with the power of log 6.7, can you evaluate this? Do you have a match? And the answer to that appears to be no, till you look a little more closely and remember that, okay, if that's a 10, what is my base of my log right here? What's the base? Do you know it? Well, if you don't see it, it's understood to be 10. Now these do match. So I can ignore these two elements here, and I'm left with an evaluation of 6.7. So very simply, look to see if the base of the power matches the base of the log, and just go ahead and give the expression that's left next to the log, and that is your answer. Our final special log value is the easiest. If I do a quick rewrite on this particular problem and I write b to the 0 equals 1, I think it's going to be very clear to you that anytime you have a base b of 1 and you have the 1 as the number, you're always going to get an answer of 0, which I just proved to you right over here. So in our example that we have for this particular problem, we're going to evaluate log base 4 of 1. As soon as you hear or see of 1, the answer is 0. And that is it. Now we're moving on to something that's more familiar to you, and that is finding the inverse of something. Because back in 7.4, we did this. Do you happen to remember? Y equals 3x plus 2. If we were asked to find the inverse of that, we would simply change where the x and the y are, and it would look like x equals 3y plus 2. Then we have to get y by itself, so we'll subtract 2 from both sides. And then we have to divide out the 3, and it would get y equals x minus 2 over 3, and that would be the inverse. Now, what would we do here if we had in example 1, y equals log base 3 of x? We would have to go ahead and take this and write it so that it's x equals log base 3 of y. Now, since we have to get y by itself, something really tricky here. I'm going to rearrange this so that the log base 3 of y equals x. And maybe visually you can see now what we have to do here. Do you happen to know? We have to rewrite. And then when we rewrite this, we won't have the log anymore, and we'll be able to simplify it such that we would have the base 3 to the exponent x equals y. And that is how we find the inverse of logs. This is our answer. Now looking at our next example, y equals ln of x plus 1. We're going to find the inverse by first taking our y and making it an x. Write everything else. Don't change anything except the x becomes the y. Everything else stays the same. Now what do we have to do here? Well, to make this a little bit easier to work with, we're going to make that ln a different value. Do you know what ln equals? Do you remember? It really equals log base e. And then write everything else the same. So there you go. We took our ln and we wrote log base e. And now, just like we did in our last example, you're going to do a rewrite. And let me just make this a little bit easier for you to see. I'm just going to put everything on one side and the x on the other. And now hopefully you can see how this rewrite looks. We're going to take that base e and make it the base of the exponent, which is x, and it's going to equal the y plus 1. But you must get y alone. So if we have to get y alone, we have to keep going here, and the final answer is e to the x minus 1 equals y. This is our final answer. Now this one's a little bit tricky, so you might want to rewind and look at how I did this one over again. I'll just explain it once again. I switched my x and my y. Then I went ahead and I rewrote the ln as the log base e. And then just so visually that you can see it differently, I just simply put the log base e of y plus 1 on one side and x on the other. And then you have to do a rewrite. Don't forget to get y alone. Go ahead and give a try to finding the inverse of logs. Y equals ln of x minus 10. Work that one out. Press that pause key as you're working. Come on back and see how you did. You did a great job if you got an answer of y equals e to the x plus 10. In conclusion for today's lesson, we have 3 types of special log values. Know them and you can save lots of time. Remember that the base is 10 when no base is written. Inverses are found by switching the x and the y value. Don't forget to get y completely alone.